contains LeBron James and the number 4. The set of all cats contains Garfield and all the other cats as well. A set is a many that allows itself to be thought of as a one. Gaylord Cantor never said that. Someone just said that he said that, but he didn't really say it. A set is a gathering together into a whole of definite, distinct objects of our perception or of our thought, which are called elements of the set. He did really say that, but he said it in German. When Cantor invented set theory in the 1870s, he wasn't just making up a mathematical game for the sake of it. No. We deal with sets every day. Suppose that someone says that pile of potatoes is enormous. They're not talking about the individual potatoes. They're not saying the individual potatoes are enormous. Some of them may be quite large, but some of them are small, like fingerling potatoes. I'm going to try to find a photo of a fingerling potato or some other kinds of potatoes. Anyway, when we say that that pile of potatoes is enormous, we're talking about the pile, not the individual potatoes. And we do the same thing with objects that are not collected together spatially. The world population of cats is enormous. The cats aren't collected together in space, but we're talking about all of the cats as a whole. And we're saying that population is enormous. We're not saying that the individual cats are enormous, although some of them might be quite hefty. The paradox, the logical problem that Russell discovers in 1901 concerns one or more of the rules of set theory. So let's go through some rules real quick before we can get to the paradox. Rule number 1. Unrestricted composition. That just means we can make any sets we want. Any set that you can think of, that's a set. In the formal axiomatized version of set theory, this is called the axiom of unrestricted comprehension. You don't have to remember that. Rule number 2, set identity is determined by membership. What does this mean? It means that what makes a certain set, the set that it is just what's inside of it. It doesn't matter how we label that stuff. It doesn't matter how we label the whole set as a whole. All that matters is what's in the set. In formal axiomatized set theory, this is called the axiom of extensionality. You do not have to remember that. Rule number 3, the order of elements in a set doesn't matter. Here, for example, are two sets. The set of the number 1 and the number 2, and the set of the number 2 and the number 1. These two sets are the same set, because the order that you put the items in, the objects, it doesn't matter. Now you can see this rule, this really comes from number 2. Number 2 says that set identity is determined by membership. All that matters is who's a member, or what items are a member of the set. It doesn't matter anymore. Rule number 4, repeats don't change anything. This set right here, which contains the number 1, the number 2, and the number 2, is exactly the same set that we were talking about 5 seconds ago. It's the set of just the numbers 1 and 2. If you repeat a number or a member of a set, it doesn't change the set because set identity is determined by membership. That's rule number 4, which is really just derived from rule number 2. Rule number 5, the description of the items in a set doesn't matter. For example, the set that contains just LeBron James and the set that contains all X's, all things, such that that thing is the NBA all-time scoring leader, playoffs included. I'm including the playoffs. If you only talk about the regular season, then Kareem Abdul-Jabbar, as of this recording, is still the all-time points leader. But if you include regular season and playoffs, then it's already LeBron James. Those two sets are the same set. It doesn't matter if you describe him as LeBron James or King James or the NBA all-time scoring leader. Either way, it's the same set containing the same one item in it, and that's that guy who's a basketball player. Rule number 6, the unit of any 2 or more sets is itself set. This rule just means that if you take two sets, like the set of all cats and the set of all dogs, and you combine them, and then you've got the set of all cats and dogs, well, that's a set too. This rule, number 6, comes from rule number 1. Because rule number 1 says you can just make any sets you want. So if you got two sets, and then you put them together, that's another set. You can make that one too. Rule 7, any subset is a set. A subset is just a set containing some of the items that are contained in another set. And that comes from rule 1, too. If you can make any set, then any set you've got, well, any group of those items in there, that's a subset, that's a set 2. Rule 8, a set can have just one member. This set contains one item, or one element, and that is LeBron James, 4-time NBA champion. A set with just one member is called a singleton set. One important thing to note is that this set, this singleton set, is not the same as LeBron James. LeBron James is a four-time NBA champion. This set, the singleton set containing LeBron James, is a zero-time NBA champion. It has never won an NBA championship, and it has never played a game of basketball because it is a set. This rule, rule number 8, also derives from rule number 1. If we can make any set that we want, well, then we can make a set with just one item in it. Okay, we are approaching the point where one of these rules is going to generate the paradox. It's going to blow the whole thing up. Hold on, it's coming. Rule number 9. A set can have no members. This set is called the empty set. You can write it like this with just the squiggles and nothing in between, or you can signify it with this, which is like a 0 with a line through it, which means nothing. This is an empty set, the empty set, or it's called the null set. The fact that there can be such a set just derives from rule number 1, unrestricted composition. You can make any sets you want, including a set with nothing in it. But it is derived from number 2, that set identity is determined by membership, that there's only one empty set, or only one null set. That one set is defined by the fact that it has nothing in it. So, if you have 2 sets and they're both empty, they're the same set, the null set. Now things get juicy. Rule number 10. You can have sets of sets. This just follows from number 1 as well. If you can make a set out of anything that you can think of, well, you can think of sets too, can't you? Sets can have sets in them. For example, the set of all singleton sets, you'd write it like this, which reads, the set of all x's such that x is a singleton set. That is a set of all sets. It contains the set that just includes LeBron James. It contains the set that just includes the number 17. It does not contain LeBron James, because this is the set of all singleton sets. And LeBron James is not a singleton set. He's not a set at all. He's a 4-time NBA champion. Or you could have the set of all sets, the set of all x's, such that x is a set. This, by the way, is how Frege and Russell answered that question from before. What are numbers? They thought, at least they thought until Russell's paradox just blew the whole thing up, they thought that the number 1 just is the set of all singleton sets, the set of all sets with one member. And the number 2 just is the set of all sets with 2 members. Now you might be thinking, I can't wrap my head around this. What does it really mean for the number 4 to just be a certain set? What does that really mean? Don't worry, no one really understands what that means. Not really. Anyway, it doesn't matter, because the whole thing is going to be blown up right now with the next rule, which is rule number 11. Sets can contain themselves. This one's weird, and it's going to give us the paradox, but that just comes from rule number 1 also. If you can think of it, you can throw it in a set. And so you can think of sets, and so you can throw sets in themselves. Consider, for example, the set of all cats. Does that set contain itself? No, because that set is not itself a cat. It's a set, and everything in it is a cat. So it does not contain itself. What about the set of all sets? The set of all x's such that x is a set. Does that set contain itself? Yes, that set contains all the sets, and it is itself one of those sets. So it contains itself, or the set of all the things that I'm thinking about. This set doesn't usually contain itself, but right now it does, because right now I'm thinking of that set. Let's follow the pattern of thought that Russell was following in 1901 and 1902 when he discovered this paradox. He was just thinking about and developing this idea, rule number 11, that sets can contain themselves. Think about all the sets that do not contain themselves. The singleton set with just LeBron James. Does it contain itself? No, because it just has one thing in there, and that's LeBron. Not any sets, let alone itself. The set of all cats doesn't contain itself, because it itself is a set, not a cat. The set of all singleton sets. Does that set contain itself? No, because there are a lot of singleton sets. And so the set of all singleton sets has a lot of sets in it. And so it is itself not a singleton set. It's got many, many members, many, many items in it. And so it doesn't contain itself. And then here are some sets that do contain themselves. The set of all sets. That contains itself. The set of all non-singleton sets. Yeah, that set contains itself because there are many non-singleton sets. And so that set, the set of all non-singleton sets, has many members, and so it's a non-singleton set. So because that set meets its own condition, it is inside of itself. Or the set of all sets that have been mentioned in this room, which is an endless black abyss from which I am speaking to you right now. Up until right now, that set did not include, but I just mentioned it. So now it does. Here's the next thought that Russell had in 1901. Okay, let's take all those sets that do contain themselves. Let's collect all of them together and make another set, and then the set of sets that contain themselves. Now we've got a set of those. We write it like this: the set of all x's such that x is a set that contains itself. Now let's take all of the sets that do not contain themselves, collect them together, make a set out of those. Russell thinks to himself in 1901, as he's barreling toward a paradox that's going to blow up the whole project to form the foundation of mathematics and all of science. This set that includes all of those is the set of all sets that do not contain themselves. And you write that like this: the set of all x's such that x is a set that does not contain itself. And then something happened. He realized the problem, and he wrote this problem on the left in 1902 and Frege received the letter. This is what the letter really was. Frege got the letter. He was broke physically. He had a break and had to be hospitalized upon reading this 2-page letter. And the letter answers this question: the set of all sets that do not contain themselves. This set, does it contain itself? Here it is again. The set of all x's, the set of all things, such that x is a set that does not contain itself. Does this set contain itself? Well, let's go through both possibilities. If it does, then this set is in here, it's in itself. And the only way to be in there is to meet this condition, the condition of not containing oneself. So if this set does contain itself, well then it meets this condition, and this condition says that it doesn't contain itself. If it does contain itself, then it doesn't. And consider the alternative possibility. If it doesn't contain itself, then it meets the condition. It's a set that doesn't contain itself. So if it doesn't contain itself, it meets the condition, and then it's in there, which means it contains itself. So if this set doesn't contain itself, then it does contain itself. If it doesn't, then it does. And if it does, then it doesn't. So this set both contains itself and doesn't contain itself. And that's just a contradiction. So it doesn't work. That's the paradox. Now you might be thinking, oh, okay, well, that's no problem. Set theory was just some made-up rule, right? That's how math is. We just make things up. Axioms are stipulated, which is to say made-up claims. So we just made up all these rules, including Rule 10 and Rule 11. And Rule 11 is really the source of the paradox. If you let sets contain themselves, well then, you're going to be able to formulate this set, and this set is the one that leads to the paradox. So let's just change the rules, right? Yeah. That's exactly what Russell tried to do. He tried to just change the rules of set theory. He made up some new rules, and according to his rules, sets cannot contain themselves. And that's what other mathematicians doing set theory have done, like the Zermelo-Fraenkel set theory. That's a version of set theory with some restrictions. They just get rid of Rule 11. And of course, if you get rid of Rule 11, you say that sets cannot contain themselves, well then you also have to get rid of Rule 1. Unrestricted composition, or the axiom of unrestricted comprehension, or whatever you want to call it. So that's what all the mathematicians do. But does that work? Like, can we just change the rules? Back before, when we were going through all those rules, Rule 1 and Rule 2, and all the way up to Rule 11, were we just making up the rules? No, we didn't just make up the rules. And so we can't just change them. That was me. I just said that. What I'm going to argue for the next, 2 minutes, is that the rules of set theory are not made-up rules. They're real, non-made-up, objective rules that already exist, and they govern perhaps one of the most fundamental practices of human existence, and that is meditation. Now I have to teach you some linguistics. This is going to take, 60 seconds, 90 seconds, something like that. Once I've done that, I'm going to regenerate Russell's paradox and show that it was never a paradox just for set theory. It's a paradox for all of language and thought itself. Let's go. Here is a sentence. Garfield is a cat. It contains 4 words. Grammatically speaking, though, it has 2 essential parts. It has this first part, which is called the subject of the sentence, and it has this second part, is a cat, which is called the predicate. The subject is what the sentence is about. It's about Garfield, the cat. And the predicate says something of Garfield. It says that Garfield has a certain characteristic, and that characteristic is being a cat. LeBron is the subject of this sentence. He's the thing that the sentence is about. And Dunks, here we go, is the predicate. We can say that predicates are true of certain subjects. So the predicate is a cat is true of Garfield, and the predicate Dunks is true of LeBron, and it's not true of me. What was the relationship between sets and objects? The relation was contained. Sets contain objects. The objects are in the sets. What is the relation or the relationship between predicates and subjects? Being true of. Predicates are true of, or a predicate is true of a subject. What I'm going to do now is I'm going to leverage this similarity to try to regenerate Russell's paradox. But now it's not with some made-up rules of set theory, but with some very much not made-up rules of predication. And predication, let me just remind you, is just the practice of saying things about things. So the practice of predication is ubiquitous. It is utterly widespread. We do this constantly. We do it linguistically all the time out loud, and almost every thought we have predicates something of something. Remember rule number 1, unrestricted composition? For set theory, that rule was the rule that there's a set for any imaginable collection of a thing or of things. Well, that rule seems like it just is true of predication also. There is a predicate for any imaginable characteristic of a thing. Anything that you can say about something, there's a predicate for that. Of course there is. And those rules of set theory that allowed Russell in 1901 to generate his paradox, those rules of set theory, the relevant ones, they're just true of predication too. Rule number 10 of predication. You can predicate things of predicates, just like you can have sets of sets. Well, that's true. You can predicate things of predicates. Here's a perfectly grammatical English sentence. Is a cat sounds funny. Yeah, sure, kind of. It does kind of sound funny when you think about it. Is a cat, is a cat, is a cat. Sure, it sounds funny. In this sentence, the predicate is a cat is functioning as the subject of the sentence. Sounds funny in this sentence is the predicate, and it's saying something about the subject, which is the predicate is a cat. Sure, we can do that. That's a perfectly meaningful thing to do in any natural language. We can predicate things of predicates. Yes, we can. Can you smell where this is going? Predicates can be true of themselves, just like sets can contain themselves. Is this right? I think it is. Consider, for example, the sentence, is a cat, is a cat. Is that true? No, because is a cat is a predicate. So it doesn't have a tail, it doesn't have fur. Is a cat is not a cat. But what about this one? Is a predicate is a predicate. Yes, that's true. Is a predicate is a predicate. It is. And that's a case where the predicate is a predicate is true of itself. It says of itself that it's a predicate, and it's right. So, rule number 11, predicates can be true of themselves. Some predicates, of course, are not true of themselves, like is a cat. We already saw that. Is a cat is not a cat, so that predicate is not true of itself. Dunks. Dunks doesn't dunk. Dunks is a predicate, so it can't play basketball, it can't dunk. So it's not true to say that dunks. No, false. Tastes like chicken. That's a predicate. Something can taste like chicken. Does taste like chicken taste like chicken? No, it doesn't. Taste like chicken is a predicate, so it doesn't taste like anything. But then you've got plenty of predicates that are true of themselves. Is a predicate, so is a predicate is true of itself. Is a string of words. Is a string of words. Yes, it is. So that predicate is true of itself. Typically comes at the end of a sentence. Well, typically comes at the end of a sentence does typically come at the end of a sentence. So that predicate is true of itself. Now, let's try to make a predicate that is true of all of the predicates that are true of themselves. And that predicate just is true of itself. Is true of itself. Is true of all of the predicates that are true of themselves. Fine, nothing wrong with that predicate. But then, what if we try to make a predicate that's true of all of the predicates that are not true of themselves? That predicate would be, is not true of itself. And now we're going to generate the paradox. I can't write this in a letter to Gottlob Frege because Gottlob Frege is dead. But I'm writing it in a video to you. Here's the question. Is not true of itself. This predicate, is it true of itself? Let's go through both possibilities. If it is true of itself, well then, what does it say about itself? It says that it's not true of itself. So, if this predicate is true of itself, then it's not true of itself. If it is, then it isn't. What about the alternative? If this predicate is not true of itself, then it's not true of itself. But then it meets the condition set out in itself. It has this characteristic specified by the predicate. It's not true of itself. So if it's not true of itself, well then it's true of itself. If it is true of itself, then it's not true of itself. And not true just means false. So if it is true of itself, then it's false of itself. And if it's false of itself, then it's true of itself. So it's both true and false, which is a contradiction. And this isn't a paradox that we can just escape by declaring that there is no Rule 11. In the case of set theory, yeah, maybe we could just declare that sets cannot contain themselves. But in the case of predication, which is just talking, in the case of saying things about things, we can't just declare that predicates cannot be true of themselves, because they can. This Rule 11, this just is true. And once you give me Rule 11, I'm going to generate the paradox. This is a paradox that we can't escape.
Apple Card is the perfect card for your holiday shopping. When you use Apple Card on your iPhone, you'll earn up to 3% daily cash back on every purchase, including products at Apple like a new iPhone 16 or Apple Watch Ultra. Apply now in the Wallet app on your iPhone. Subject to credit approval. Apple Card issued by Goldman Sachs Bank USA, Salt Lake City branch. Terms and more at applecard.com.
What is cosmology? Cosmology is an attempt to answer the greatest questions that ever posed to humanity. How did the universe begin? What is the universe? Why are we here? What makes up the universe? When will it all end? What's it made out of? What's the eventual fate of the universe? Is it a real? And most importantly of all of that, how can we learn anything about any of these questions? Cosmology seeks to answer these questions using experimental science and measurement to understand the origin and fate of the universe. We attempt to create models of the universe in various ways and see which ones work, which ones fit observations, and then make observations to test those ideas. And if the ideas don't fit the observations, then we have to discard the ideas. And if the observations are challenging and new, then we have to understand them with new ideas. The universe itself is very vast. It is composed of things like people and oceans and planets and stars and galaxies. And it is composed of normal matter, dark energy, and we think of the things that go from the very smallest to the very largest. And if we look at the cosmic microwave background, we look at the origin of things from the Big Bang nuclear synthesis, we look at our place in the universe. how it has changed from being thought from ancient times when we thought we were the center to now we know we are one of a multitude of galaxies in a vast cosmos. With that very brief introduction to the concept of cosmology, I'd like to welcome you. My name is Jason Gundel. I have taught cosmology at William Patterson University. I have also done quite a bit of things, as you probably see on my YouTube channel, for introductory astronomy. And so I figured I'd put my cosmology course on my YouTube channel. If you wish to follow along, you can certainly do so. I am utilizing as my basis Dr. Barbara Ryden's textbook, Introduction to Cosmology. She's a professor at Ohio State University, and I've used her textbook in my course at William Patterson University in the past. So, why am I doing this? Principally because cosmology is really enjoyable to me. It's what I have a master's degree in, and I find it a fascinating subject. So what should you expect? We're going to go through this textbook. We're going to hit every single chapter and every single section of it. I'm going to derive mathematical equations and give you the theoretical and observational understanding for what cosmology is and where and what we all can understand from it. In order to understand anything about the cosmos, we have to understand how to measure it. Because in any science, no matter what it is, you have to be able to measure things. You have to have reliable ways of measuring those things, and the degree of which you're going to measure them. So part of the agreement of understanding measurement is the units that we use to measure things by. And the standard thing that we're going to talk about, some basic units to begin with as this introduction. We will introduce the idea of distance. We know about meters. Meters are 1 meter long. Most of the world knows what a meter is, but in the United States we like to look at yards and meters. But we're going to stick with meters. And the meter is a standard sort of human-sized distance, and the kilometer is a standard human-sized distance. But the real astronomical distances start when we look at the astronomical unit, with an average distance between the Earth and the Sun. That is 1.5 times 10 to the 8th kilometers, or 150 million kilometers. The next most interesting thing from the astronomical unit for a unit of distance is the light year. And that's mostly a kind of a cultural thing. It is the distance that light will travel in a year, which is about 10 to the 13th kilometers. More important than the light year is the parsec. The parsec is a geometrically derived observational distance to something that's very far away. A parsec stands for a parallax of 1 arc second. So what's that mean? Parallax is that apparent shift that you see in something when you, say, hold your thumb. Let's say that something is your thumb, and you hold it at arm's length, and you blink your eyes left and right, and your thumb appears to shift in position with respect to background things. Now, that shift might be big. It might be a degree or so, and the distance between your two observation points, your eyes, is only 2 inches. Let's say now the observation points are separated by 1 astronomical unit, and the angular shift of your thumb is now 1 arc second, and not a degree or 2 or 5, but not even half a degree, not even a tenth of a degree, but 1/3,600th of a degree. And that means that it's going to be very far away because that shift will be very small, and the baseline is very large, so you're going to have to be really far away such that a really large baseline, 1 astronomical unit, will give you a very small shift. And that ends up being about 3 1/4 light years, or 206,264 astronomical units. That's the distance. This is a geometric distance, and so there it's a direct observational, and therefore it's really important and better than light year because photons don't have clocks attached to them, so a light year is really kind of meaningless. So this is the main geometric measurable distance to the stars. And the typical distance between stars is about a parsec or so. But when we think of the largest collections of stars, like the Milky Way or galaxies, we have to start measuring the distance.
As you may have heard, this year there are 4 incredible new iPhones, and they're all built for Apple Intelligence. iPhone 16, iPhone 16 Plus, iPhone 16 Pro, and iPhone 16 Pro Max. These new iPhone 16 models have been redesigned, inside and out. From the colorful iPhone 16 and iPhone 16 Plus to the titanium iPhone 16 Pro and iPhone 16 Pro Max. I'm going to explain the differences between them. iPhone 16 and iPhone 16 Plus feature a new rear camera design and come in white, black, teal, pink, and ultramarine. iPhone 16 Pro and iPhone 16 Pro Max are made with titanium and
to galaxies in terms of megaparsecs, 10 to the 6 parsecs. And then when we think of distances or size scales of galaxy clusters or distances between clusters, we start thinking in terms of gigaparsecs or billions of parsecs. For some basic ideas, the distance to the nearest star is about 1 1/3 parsecs. The distance to M31, the Andromeda Galaxy, is about 3/4 of a megaparsec. And the Virgo cluster of galaxies is about 16 or 17 megaparsecs. The size of the observable universe, the size from if we look in one direction and turn our heads 180 degrees and look in the other direction, that is the observable universe, and that goes in any direction which we look one way or the other. And the diameter of that is approximately 28 or 29 gigaparsecs. So these units of distance are very large. The next unit we'll talk about is the amount of stuff there is in a place, and that stuff is about mass, and mass has a very interesting set of properties. But we will first say that we'll kind of agree that we understand what mass is, and that it is some accumulation of stuff. And the standard unit in the SI units is the kilogram. And kilograms are pretty important, but for astronomical and cosmological purposes, they are not. More importantly, we use the solar mass, or the mass of the sun, which is about 2 times 10 to the 30th kilograms, which is a lot. And the mass of our Milky Way galaxy is about 1 trillion solar masses, and the mass of the Virgo cluster of galaxies is approximately 10 to the 15th solar masses. The solar mass is a very good unit, but we can see that galaxy masses can be somewhere between billion or very tiny galaxies on 1 million or so solar masses, up to trillions of solar masses for very large stuff. So our unit is going to be the solar mass for our base unit measurement. Just as important as mass and distance is time. Time is really important for physics because it doesn't matter if there's a thing over there that has mass and it's over there at that distance. We want to know how things work, and so things work means that there must be some time that's involved. And in the units of time that we know are, of course, seconds, which are like a second minute of an hour, which is a very interesting way of thinking about it historically. And finally, we will continue with the idea of the second as in the Earth here, the time it takes the Earth to go around the sun, which is about 31.5 million seconds, or pi times 10 to the 7th seconds, which is really close to pi times 10 to the 7th seconds, which is fascinating. Anyway, but cosmologically, that's not very important. The second, even the year isn't important. Cosmologically, we more think of things in millions of years, like mega years, 10 to the 6th years, or giga years, 10 to the 9th years. The age of the Earth is about 4.567 giga years. The age of the Milky Way is approximately 13.5 giga years. And a characteristic age for the universe, which we call the Hubble time, is about 14.7 giga years. And these are the types of time units that we care about cosmologically. We really do care about millions of years and billions of years in cosmology. Now, once you take some stuff that has mass and it's over there and it is moved from there to here, it takes energy and work to move things from here to there, and so we have to then define also the units of energy and power. The standard SI unit is the joule, and or we can also call it a Newton meter. And the units on the units of energy are different because they're made up of mass and distance and time. The unit of energy is a kilogram times a meter squared over a second squared, or a Newton meter, which is a unit of force, which is a kilogram meter per second squared, exerted through a meter. That is the unit of the Newton meter, joules in terms of in terms of the base units of mass, time, and distance. So the watt is 1 joule per second, which is another SI unit. And next we have the good astronomical unit of the solar luminosity, or how much energy the sun is putting out every second. That's about 4 times 10 to the 26 watts, which radically dwarfs the entire output of humanity, which is on the order of some numbers of hundreds or thousands of terawatts, which is only 10 to the 12. So the sun puts out a lot more energy than humanity ever will. The luminosity of the Milky Way can then be measured in solar luminosities at about 3 times 10 to the 10th solar luminosities. And you can have extraordinarily bright objects that can be seen from